actually the bulk of the material we'll get through today, but we'll see what happens. Alrighty, so our objective is going to be able to describe catalysts, calculate K values, and describe equilibrium. And I forgot to record my 6th period, and I had to have a video for today, so I made myself a note. Alrighty, so while I'm thinking about it, is we will do Lab 6 on Friday. And that is 12/4. So make sure you come to class prepared on Friday to do lab number, and that's Lab 6. That's the one we were supposed to do with Chapter 5. Okay, I want to get it out of the way, and then we'll make some things work. Okay? Alrighty, so reaction rates.
Mr.
Yes.
In the objective, what does it say? It says calculate.
It's called, it's K values. That's a K values. We're going to talk at length about that. It'll make sense, okay, Alvin? Alrighty, so reaction rates. Now, what we're going to do is when you talk about a reaction rate, a rate is basically just a speed with how fast a reaction happens, right? Does anybody know what I can do to increase reaction rates? If I want to increase rates, what can I do?
Increase the temperature.
Increase the temperature. That's probably number one, right? Increase the temperature. That's why you boil the water to make your jello, right? It makes that jello dissolve faster, right? What else?
Increase the amount of reactants.
I can add a catalyst, or I can increase the concentration of reactants. Okay, they are the 3 easiest things. Okay, temperature's obvious. That's something you've done pretty much all your life. Okay, concentration we will talk about a little bit. Now catalysts. Okay, if you go back to this, okay, anybody remember what this was called from the other day? Nobody?
Energy diagram.
It's called an energy diagram, right? Okay, and if this is my regular energy diagram, and I'm going to take my red one and I'm going to have a catalyst now, this is what it's going to look like. I always screw this side up, so I'm going to turn this a little bit. Okay, now, what a catalyst does, okay, a catalyst speeds it up, speeds the reaction up by doing what? And remember what that hump represented? Yeah, by lowering the energy of activation. Okay? And I mean that makes sense, right? If I've got to climb a mountain, that's going to take me a long time, right? If I'm only going to climb a little hill, it's going to take me way less time, right? So by adding a catalyst, I can speed up the reaction because it lowers the activation energy. Now, where does a catalyst belong? Is a catalyst a product or is a catalyst a reactant?
Neither, it just stays the same.
Yeah, a catalyst is neither product or reactant. In fact, most catalysts you can use over and over and over again because they are not part of the reaction. They simply give the reaction a mechanism to happen at a lower reaction rate, which allows it to happen faster. Let's face it, in the world of business, if I'm making things, do I want to take a long time to make something? No, I want to make it as fast as I can, right? Because the faster I make it, the more what? The thing that makes the world go, the more money I make, right? And we all want to make more money, okay? So yeah, now, there's several questions about this on the test. One thing you need to understand is that notice these end at the same exact point, which means a catalyst does not affect my what? Then remember what this was down here?
It doesn't affect your H value.
Yeah, it doesn't affect my delta H at all. Okay, it simply lowers the hill I have to climb. Okay? Now, with that being said, we need to talk about equilibrium. Now, I don't know why it is, but this is one of the hardest things for my students to understand. Okay, equilibrium. I think it's because we're not used to equilibrium reactions. Okay, we're used to reactions that I start with the product, I end with the reactant, and that's it. Equilibrium is a state in which both the forward and reverse reaction are happening at the same rate. So typically what you see, or you don't see anything. You don't think anything's happening because it's happening on a molecular level. But what's really going on is that you're going right and you're going left. It's like, do you guys know what a terrarium is? Anybody know what a terrarium is? Nobody? Think, everybody knows what an aquarium is, right? Where you put your fish, right? Well, a terrarium is where you take that fish tank and you fill it full of dirt and you put plants in there. And then you seal it up. And it's kind of a closed system, meaning that the water that's in there cycles. Okay? Meaning sometimes it's liquid water, sometimes it's water vapor, right? Now, in an equilibrium situation, you end up with double-headed arrows. So I'm just going to make something up. Let's say I got 3A plus 2B is in equilibrium with 4C plus 1D. Doesn't matter. Here's a reaction. These two arrows means that an equilibrium is established. What that means is for every time these two generate those things, these things go back and generate those things. So for every water molecule that becomes a gas molecule, there's a gas molecule that does what?
Becomes a water molecule.
Yeah, condenses and becomes a water molecule. Okay? Now, equilibrium is important especially in industry. Okay? As a consumer, you just don't see it very much, which I think is why it's hard for students to grasp this concept. Okay? Now, what they're going to do is they're going to introduce you to what is called K. K is what is known as the equilibrium constant. Okay? And it is the products over the reactants. But it's in a very specific way. Okay? It's going to look like this. Okay? Now, notice this exponent. Where did I get that exponent?
From the coefficient.
From the coefficient, right? Now, does anybody remember what brackets meant? I know we've used them a couple of times. One was on polyatomic ions, where we drew their Lewis structures. That is not the same kind of brackets we're talking about. This is, I'm going to be honest, I don't even remember if we have talked about this. Brackets means concentration. Okay? And what they'll do is they'll give you something like this. They'll say that, you know, A has a concentration of 0.30, B has a concentration of 0.70, C has a concentration of 0.25, and D has a concentration of 0.94, something like that, right? Okay. Now, then they'll simply say to find K. Now, if you have a calculator at home, you need to do this. We had some problems in my last class, all coming up with the same value. Okay? So what it's going to be is it's going to be your product. So C and D are in my numerator. So it's going to be 0.25 to the fourth, right? 0.94 to the first, divided by 0.30 to the third, and 0.70 to the second. Okay? So what I would do is I would take parentheses, type that in, hit the divide key, put parentheses, type that in, and hit enter, and it usually spits out the right value.
It's 0.28.
0.28. Anybody else get 0.28?
Yeah, I did.
Yeah, 0.28. Alrighty, now,
Yeah.
then, that's an 8, right? Then they'll say, okay, that's my K. And then they'll ask you, what does that K tell me? Okay, and there's 3 values you can have for K. You can have a K that is greater than 1, you can have a K that is less than 1, or you can have a K that equals 1. Okay, if your K is greater than 1, it means it favors the products. Okay, if you've got a K that is less than 1, it favors the reactants. If you did I say K equals 0? Or did I say K equals 1? Anybody recall?
I think he said K equals 1.
Okay, that's what it's supposed to be. I don't know why I wrote a 0. K equals 1 is then this favors neither. And what that tells you is it tells you which side of this reaction this lies on. Okay, so what this means is that if I mix whatever A and B are, this K is kind of small, right? What that tells me is that am I going to get very much C and D? I'm not. Okay, it tells me that I'm going to be mostly A and B still. If K was big, like let's say K was 50, what that tells me is that I'm going to get a whole bunch of this, and there won't be very much of this left over. Does that make sense? Okay? And you just got to remember that equilibrium is always back and forth. The value of K simply tells you how much back and forth there is. The higher it is, the more forth there is. The lower it is, the more back it is. Does that make sense? Or no?
So would this be for like all reactions or just like...
Okay, so it's got to be an equilibrium reaction. It's got to have double arrows. Okay, and now, so, who was that, Higley? Who asked that question?
Yeah.
Okay, so here is what I was thinking. Okay, like let's say, like look at fire. Okay, we've all built a fire, right? Okay, combustion is not an equilibrium reaction. I start that sucker, it's going to burn until it goes out, right? So it's only going one direction. Okay. Most reactions that we deal with on a daily basis only go one direction. Okay, I mix up a cake and I put it in the oven and I bake that cake. Can I go backwards? Can I go back to the batter again? I can't. So most things only go one direction in, a regular human's world. In the chemistry world, a lot of things go back and forth. Okay? And so what they're going to do is they're going to say, okay, here is a back and forth reaction signified by the double arrows. Then I can go and say, okay, now that I know that, I can go and calculate K. I can go, does that make sense? They've got to tell you that. So now what they're going to do, and this is important, because there's lots of these on the test. Well, I shouldn't say that. There's like 3 or 4 of these. So if I say I've got 2A plus 3B, and I'm in equilibrium with 4C plus 5D. Okay, let's say this is my reaction, right? Now, let's say I'm in business and my business is making C. I sell C. D would be a byproduct. But let's say I'm selling C, right? So I mix my two chemicals A and B together, and they're gonna react, and they're gonna start to produce C and D, right? After a while, though, I'm gonna have enough C and D that this reaction is gonna start doing what? Yeah, it's gonna start going back the other way, right? Okay. So what they do is they say, well, if this reaction goes that way, does that help me as a company? It doesn't, because I want as much C as possible. So what do? Does anyone know what that company's going to do?
They're gonna like pipe away the C.
Exactly. They are going to remove the C as it's made. Because if I remove that C, that means there's none of this to react to go back that direction, right? So I'm going to take the C out and I'm going to sell it. Okay, eventually I'm going to end up with these great big pile of D that I'm eventually going to go and bury out in the desert, right? So what happens is that when you look at this equilibrium equation, you've got to look at it and say, okay, if I want C and I'm going to remove it, what is going to happen to the amount of A and B I have left over? Let's say I give this 5 hours, and I'm constantly taking my C out. What's going to happen to the amount of A and B I have? Yeah, England, right? They're going to continually do what? They're going to go down. What's going to happen to the amount of D I have?
It's gonna go up.
It's going to go up. Which way is my equation going to shift? Is it going to shift it back this way, or is it going to shift it that way?
Towards the reactants.
It's going to go towards the reactants?
Well, by the way you said it, I'm assuming no.
No, exactly. Because look, these are going down, right? Which means it's favoring the products because we said it's going to continually try to do what with this? As I take it out, it's going to say to itself, crap, now I've got to do what?
Make more.
I got to make more. Exactly. I've got to replace that. Okay, the analogy I used to use really wasn't very good, but watch. So let's say I've got 3 flours plus 4 chocolate chips. 4 chocolate chips, right? And I want to make, 5 cookies over here. Okay? Now, let's say I mix this up and I bake my cookies, right? The minute I pull my cookies out of the oven, my little brother comes in and he eats them. So my amount of cookies I have is going down. Well, what does that mean you're going to have to do?
Make more.
You're going to have to replace those cookies he ate, right? Well, what's that going to do to the amount of flour and chocolate chips I have in my house? It's going to go down, isn't it? Because I'm going to take them and I'm going to turn them into that. So it's going to take it and it's going to put it that way. Now what you'll notice is that if I have things on opposite sides, and it's what I'm talking about, the arrows are going the same direction. But if I go back to this one, now the arrows are going in opposite directions because they are on the same side now. So by removing C, wouldn't I be going down like that? Okay. Now, so if I did this, let's say I've got, 4A plus 5B is in equilibrium with 2C plus 6D. Okay, let's say I did this. And let's say I remove A. I take A out. Okay. Now this is after this has reached an equilibrium. So I've let this react a while and it's all, going back and forth now. And let's say I take some of my A out. So my A is going to go down, right? Okay, what's going to happen to the amount of B in my container? going to go up. Why?
Because the equation is constantly trying to reach equilibrium.
Exactly. It's constantly trying to reach equilibrium, which means if, as I'm taking this out, these two things are going to try and do what? What do they want to do with this? Starts with an R.
Equal.
No, they want to... Did you say replace?
No.
They want to replace it, which means it's now going to go this direction. What's going to happen to the amount of C and D in my container now?
Down.
They're going to go down. Okay? And this works with any equilibrium equation. They're going to say, given the following equation, let's say I remove B. What's going to happen? Given the following equation, let's say I add B. What's going to happen? And you've got to look at it. So let's say I do this exact same thing in red. And let's say I add B. I'm just going to add some B. New equation. I'm adding B. Okay? Which means my B is going to go up. Okay, what's that going to do to my C and D?
They're going to go up as well.
They're going to go up because they're on the other side, right? Because it wants to compensate, so it's going to drive it that direction. What's that going to do to my amount of A that's left?
Go down.
Yeah, because when they're on the same side, they're opposites, it's going to go down. Okay? Does that make any sense?
Yes, it does.
Okay, now, let's say I wanted to write a K equation for that. What would my K equation for that reaction be? Just a minute. Can you guys still see my screen?
Yes.
Okay.
Yeah.
Jonah, did you make it in? If you guys don't get in on your Chromebook, I have to let you in. Anybody see Jonah? He was asking to get let in. No? Huh. Alrighty.
I
So
saw him leave.
I know.
He was in the meeting at one point.
Yeah, it must have kicked him out, so he had to get on something else to try to get in. I hit admit, but I don't know that it worked. So you guys understand that because your Chromebooks are all on the same system, it makes this automatic. But if you log in like on your phone or something, it sends me a message and says, hey, so-and-so wants in, then I have to let you in, and it doesn't always work for some reason. So, alright, anybody got my...
I'm on my phone right now.
Oh, okay. He must have got in because I'm back up to 31.
I just used my school email, so.
Oh, I got you. Okay, so does anybody have me a K equation for this yet?
Yep, it'd be K equals C brackets squared times D to the 6th over A to the 4th times B to the 5th.
Just like that. Okay. And there's probably, between those two questions, six of those on the test. Just like that. Okay.
Okay, wait, I have a weird question.
Go for it.
So with that equation, where it can go either way,
Yes.
would it also be okay if you inverted it because you still have the products on top, you're just going a different direction?
Yes. Be really, really careful when you do that, though. Okay? Because what you'll see is a lot of them are going to be written. Let me show you another thing they'll do here. Let's say I go, 2A plus 3B is in equilibrium with 4C plus 2D. But now I tell you that this is exothermic. Okay? Now, Once you know that this is exothermic, what do you know about this reaction? Anybody remember?
There's like energy leaving.
There's energy leaving, right? Which means energy is kind of a what in that sense?
The product.
Exactly. So I would go plus, let's say I said heat here, right? Now it becomes, you've got to be really specific about what happens here. So look, let's say I take this reaction as it's written and I put it in the fridge. Does anybody know what it's going to do to that? By putting it in the fridge, what am I doing?
Slowing it down.
Well, it depends. This is exothermic, right? Okay, okay, what you need to understand is it might slow it down, you're right, but it's still going to reach this equilibrium. It would just take longer. Because you're talking the reaction rates we started this discussion with, right?
Uh-huh.
Yeah, it would slow it down, but it's still going to reach this. It would just take what?
Longer.
It'd take longer, okay? I'm saying once I've reached equilibrium, if I put this in the fridge, what am I going to be doing to the heat in this reaction?
You're going to be taking it away.
I'm going to be taking it away. It's going to go down, right? What's that going to do to the amount of C and D that are produced?
It's going to go up.
Yeah, they're going to go up. What's going to happen to the amount of A and B I have?
They're going to go down.
They're going to go down. Again, on the opposite sides are the same. On the same side, they're going to be different. So it just depends. And they can put it as exo, they can put it as endo. There's a lot of little different things they can tweak these, but the idea doesn't change. Just to understand, if it's exothermic, my heat's a product. If it's endothermic, my heat's a reactant. And then you really can't swap it. Does that make sense, Higley? Got to be kind of careful.
Yeah.
Okay. Alrighty. Now, with that being said, we must review this. Okay? So, and we only got 9 minutes. We need to hurry. Alright. So,
Can you slide the paper up so that we can see it?
sorry. It's actually down, but yeah. Alrighty, so here is my reaction. Now, again, first thing I would always do is what? Anybody know? I would always balance it, right? But in this situation, it really doesn't matter because they've already told me right here that no matter what happens, that for every 1 mole of this I burn, I'm going to produce that many kilojoules. Doesn't matter. Okay? The other one, the other day, I had a 2 here, but it still didn't change this, that it was kilojoules per mole. So, how am I going to figure out how much energy is released if they give it to me in grams? Who remembers where we went very first?
You'd have to convert grams to moles.
Okay, and how would I do that? What's going to go in my numerator? The molar mass is in my numerator?
No.
No, the molar mass is in my Denominator, right? So I'm going to go 1 mole of C3H8 in my numerator. What's going to go in my denominator then?
44.097.
44.097 grams of C3H8, right? What's going next?
The H value.
The H value, right? What's going to go where?
The negative 212.7 is going to go with the numerator and the 1 mole in the denominator.
Right, because that's kilojoules per 1 mole, right? So my moles of C3H8 reduce out. My grams of C3H8 reduce out. Somebody get me an answer. Did anybody balance this by chance?
Yeah, I did.
What did you get?
The 1534.
Anybody else get that, or did I only have one student balance it? Okay, we're good? Alrighty. So now, who's got this answer right here?
I got 615.5.
615.5 kilojoules? Well, where did that negative go?
Well, you can't have negative energy, right?
Okay, I can't release negative energy. Okay?
Oh.
When they use the word released, when they use the word given off, when they use any words like that, they're already taking that negative into account, so you're absolutely correct. That will be a positive value. Okay, just understand this, that when you answer this question, you know, a lot of you, if you do the math exactly like it's written, that's going to be a negative value. You're going to look at the answers and you're going to realize, well, my number's there, but theirs is positive. And then you're going to say, oh, wait, Mr. Denton said, and I'm going to go, yeah, that's what I said. You guys see what I'm saying? Make sure you understand that if they use the term released or given off or produced or I don't know what other words they might use, that sucker is going to be positive every time. Now, the question I have is this. As I look at that, that should look familiar, shouldn't it? Is that really any different than what we did last chapter? No, the only difference is there's no what here. What didn't we use in here? That we used a lot last chapter. Yeah, we use that molar ratio a lot. And here, yeah, there's no mole to mole in this, but it's still the same, you know, dimensional analysis, stoichiometry type stuff. Okay? So, you know, just if you got it, this stuff's easy. If you didn't get that last stuff, you're in trouble. Okay? Now, that is the discussion today. So remind yourself that we're going to do, yeah, I've got one more problem, but we're not going to have enough time. Let's do this. Do this on your own and bring it to class. So I'm going to go this. How much energy same